So my day job is assistant professor at London School of Hygiene and Tropical Medicine. My background's in maths. I specialise in mathematical modelling of infectious disease. But I also write about maths and science, and most recently this book about the relationship between maths and gambling. I guess in the face of it, my day job couldn't really be much further from this world of casinos and playing cards and plastic chips. Sorry? Exactly, yes. Well, this is what I'm going to get to, is that actually gambling and maths and science have this incredibly intertwined relationship and a very long-standing history, and that's what I want to talk about this evening, how the two have interacted. Now, as I'm talking about gambling, I always think it's good to start with an example of how not to gamble. This is a story from a few years ago, and as you can pretty clearly see, there's two large flaws with this lady's strategy. I mean, firstly, it's completely illegal, and secondly, clearly doesn't work. I think anyone who's come across these stories of get rich quick and beat the system will have encountered these two themes incredibly frequently, that either you've got something a bit dodgy going on, or ultimately it's a system that when you break it down isn't one that's going to work. And what I want to do today is tell you a little bit about the history and some of the ideas which have taken a third approach, which have actually used ideas from mathematics to take on these games and ultimately beat them, but also how the ideas have flowed the other way, how actually a lot of ideas from games of chance have inspired many of the concepts which are now fundamental to a lot of the work we do in the mathematical sciences. And I want to stick with lotteries for a moment, because there was a story about lotteries years ago that first got me interested in the maths of betting. Now, of course, anyone who's thought about lotteries, played lotteries, it's pretty easy to spot the odds are not in your favour. It's extremely difficult to win. But even the way in which we measure how difficult it is to win is a relatively recent development. If you look at the history of maths, it goes back millennia, but really probability theory is something we've only seen develop in the last few centuries. And one of the pioneers of this was in Renaissance Italy, a gentleman called Girolamo Cardano. He was a physician by training. He was actually the first to describe the clinical symptoms of typhoid. And he was also a keen gambler. And to our knowledge, was one of the first to outline a lot of the mathematical theories for the game. And one of the things he described is what we now know as a sample space. So if you're interested in probability, you need some way of outlining your possible range of events so you can quantify the ones that you're interested in. Now, going back to lotteries, for the UK lottery, there was a recent change a couple of years ago, which means you're picking 6 numbers from a possible 59. So this gives you 45 million combinations of numbers. Clearly something that's impractical from a point of view to buy them all up. But if you did, let's just run with that for a chance. Suppose you buy up all 45 million tickets for the lottery. Each one of those costs £2, so for £90 million you could, in theory, buy the jackpot. Now, the jackpot is never that big, so it's really not a strategy which is worthwhile doing in the UK, but not all lotteries are the same. Back in the early 90s, the Irish National Lottery had 1.94 million combinations. And what's more, each of those tickets was only 50p. So actually, to buy up every single possible combination of numbers in that lottery would cost you less than £1 million. Again, in most weeks, the lottery jackpot wasn't going to be that big, so it wasn't worth doing. But if a rollover came around and it was large enough, potentially that was a strategy that would be worth doing. And a syndicate in Dublin spotted this and decided to put it into action. They collected up hundreds of thousands of blank lottery tickets and by hand filled out every single one of those 1.94 million combinations. And then waited for about 6 months until the bank holiday of May 1992, when the jackpot hit 2.2 million. And then they put their plan into action with all these stockpiled tickets, went from shop to shop, buying up as many as they could. Now, shops that would sometimes sell hundreds were suddenly selling thousands. The lottery spotted what was going on, obviously weren't very impressed about it. Although it's completely legal, the lottery tried to clamp down. And as a result, the team, by the time the draw came around, had only bought up about 80% of the combinations they needed. So still quite an element of luck involved in their strategy. Fortunately for them, the numbers they'd bought were included in the ones that came up in the jackpot. Unfortunately for them, there were 2 other winners that week. But actually, when you add up, when you take the jackpot they won, they matched 5, they matched 4, all these sub-combinations of numbers, they walked away with a profit of about £300,000. And for me, when I heard that story years ago, it was just this brilliant example of an incredibly simple bit of maths and just this huge dose of sheer hard work and audacity, and they'd taken on a system that's supposedly unbeatable and shown how you could tackle it. Now, of course, that insight, just brute force attacking a lottery, is nice, but mathematically not very interesting. But there's a lot more features of lotteries that can also be examined. So one of them is what's known as Lotto designs, this idea that if you want to guarantee, for example, take the Old English National Lottery, where you pick 6 numbers out of a possible 49. If you want to guarantee matching, say, 2 numbers, what's the minimum set of tickets you need to buy? It turns out for a 6 out of 49 lottery, the minimum is 19. So just to give you an example, this is a Lotto design for a 6 out of 49 lottery. If you buy up that combination of numbers, you're guaranteed that you'll match at least 2. And people have done this for a lot of other different formats of lotteries as well. But one of the things that's remarkable is how many tickets would you need to buy to match 3, or guarantee you'll match 3 numbers out of that collection of 49. It turns out that that's actually an open problem. No one actually knows exactly what the minimum is if you want to guarantee matching 3. People have computationally done it. They've just brute force found Lotto designs that work. There's one that's, I think the smallest to date is about 163 tickets, which would guarantee you matching 3, but there's no proof that that's a lower bound. And I think that really emphasizes just the sheer complexity of combinations involved in these kind of lotteries, that really even getting insights into matching 3 numbers is something which is incredibly challenging. So that's modern lottery research. But as I mentioned with Cardano, there's really a long history of people researching these kind of games. And Cardano was in the 16th century, but actually even continuing further into the future, people were also interested in games and using that to shape ideas about maths. A famous example was in the 17th century. A writer, Antoine Gambard, was interested in this class of problems, known as a problem of points. So to give you a kind of toy example, say we're playing a game where we flip a coin repeatedly. The first to win 6 tosses in total gets 100 quid. We abandon the game for some reason, and you're 5-3 up. How much money should you get? So a relatively simple problem, but one for him that there wasn't a kind of satisfactory way of finding an answer. So he got in touch with Blaise Pascal, who's an acquaintance of his, and Pascal in turn collaborated with Pierre de Fermat on this kind of question of how do you essentially calculate the value of each player's position in this game. And the ideas they developed in tackling these kinds of games laid the foundations for what we now know as expected value. If you want to work out the mathematical expectation of a game or situation, then you just need to essentially sum over the probabilities weighted by the expected payoff. So in this case, we abandon the game with you 5-3 up. The only way in this situation that I can win the game, if you haven't spotted it already, is for me to get 3 tosses correct in a row. Probability of that is 1 in 8. So in other words, the other 7/8 times you would win the game. So the value of the game to you should be £100 times 7/8 in that situation. So a relatively simple problem, but one that inspired really kind of a lot of thinking that's fundamental now to how we approach mathematical problems. But the developments continued. In the 18th century, a number of people became interested in problems where expectation tended to lead people astray. If you come across things like the St. Petersburg paradox, there are these games where the expectation for a player was positive, or in some cases infinite, and yet players wouldn't value the game in that way. So it seemed there was this disjoint between actually people's perception of how much something's worth versus this kind of expected long-term behavior. And to get around this, mathematicians like Daniel Bernoulli developed the early ideas of utility theory, that really the value of a situation depends our relative valuation of it depends on how much money we have and how much money we might potentially gain. And the insurance industry is the simplest example of utility, that you don't insure something if it's cheap, but if it's very valuable to you, you'd rather take that monthly loss. Your expectation is negative, but you don't want this uncertain impact of having something being lost or stolen. So really kind of these ideas continue to shape people's thinking about these problems. And again, it continued even into the early 20th century. This gentleman, Henri Poincaré, I'm sure familiar to most, if not all of you, he was also very interested in the ideas of prediction, and in the early 20th century wrote a couple of really nice books outlining his ideas about this. And as he saw it, really unexpected outcomes were a product of ignorance, and he categorized these situations by what he called the levels of ignorance. And the first of these was a situation where we know what the rules are, we have the information, and we have to do some rudimentary calculations to get our answer for a particular event. So a classic, if you've got a very simple physics problem and you've got the initial conditions, that's not something that would take you a huge amount of time to get a solution to. The second level of ignorance, he said, was a situation where we know in theory what the rules are, but we lack the information necessary to make accurate predictions. And he used two examples. One was a roulette table, and a related one was the distribution of asteroids along the zodiac. Was this idea of bodies rotating around a point. And he made the following statement, that in these kind of situations, our ignorance of the initial conditions can have a very large effect later on. In the case of a roulette ball, a very small change in its initial speed will have a huge effect later on. Now, of course, this is just sensitive dependence on initial conditions. And years later, in the 60s, this is something that, through Lorentz and subsequent work, would become the foundations of chaos theory. But it was really the initial seeds of that idea being sowed through Poincaré and his work on these games of chance and related situations. But of course, that was just the second level. He also pointed out that there was a third level of ignorance where we either didn't know what the rules were, we didn't know what the physical laws were for a particular system, or perhaps they were just too complicated to fully unravel. In this situation, all we can really do is observe and try and make inferences on our observations. And it was this level of ignorance when gamblers first started taking on roulette tables they worked with. So rather than trying to predict the physics of the table, they instead just thought, let's watch tables. Over time, tables can perhaps become biased or wear down or uneven. So these gamblers would just watch the table and look for something that seemed a bit odd. But that raises the question, of course, of what do we mean by odd? How do we measure evidence for something that's unusual? And while Poincaré was thinking about roulettes in France, on the other side of the channel at the same time, this gentleman, Karl Pearson, was also thinking about roulette. And he was starting his early work on statistics and really wanted as much random data as he could get his hands on. He once spent his summer holiday flipping a coin 25,000 times to gather a random data set to test his new methods on. In some cases, he got his students to do the work, which is, as I'm sure you know, cuts a few corners. But he wasn't just generating data. He actually, fortunately, found an example of a random data set that he could analyze, and this was in the newspaper Le Monaco. They would publish the results of roulette spins at the tables of the casinos of Monte Carlo. For him, this was just a perfect data set to analyze because you had all of this random data. He collected, I think, about 15,000 spins, and you could look to see if these tables are truly random. So he studied a few different properties. One of them was how often black and red appear. Now, of course, if you take away the zero, the green zero, you'd expect it to be evenly distributed, 50-50 between the two. Over the course of these 15,000 spins, red came up, he found, I think it was 50.15% of the time. And he observed that, although this is a deviation from what you'd expect, over that number of spins, it wasn't sufficient to reject the idea that the table was indeed unbiased. Then he looked at more things in detail. He also looked at how often strings of the same color appear. Of course, if you've got a truly random process, you sometimes expect strings of the same color to appear purely by chance, and the bigger your data set, the longer your strings might be. But Pearson found that actually black and red switched far too often in his data. And he actually noted that had he been observing these tables since the geological start of time on Earth, he would not have expected a result that extreme. Made him quite angry that his lovely laboratory wasn't producing random data, and he actually suggested that casinos be closed down and that the proceeds naturally be donated to science and mathematics. But it turned out something a little bit close to home was happening. Those journalists from Monaco, rather than sitting by the tables and watching and recording the numbers, had instead been sitting in the bar and making them up. And that was why, of course, when he ran this statistical analysis, he found that it wasn't random data, because humans, of course, aren't very good at generating this volume of truly random data. But needless, that was really the early ideas of hypothesis testing. A lot of his work here, if you think, he's saying the chance of observing an event that extreme, given that this hypothesis, the table is unbiased. that work would eventually shape his ideas on the chi-square test and on p-values, and this ability to quantify whether you believe there's sufficient evidence to accept or reject now a hypothesis. And of course, this is fundamental in modern science. For good or for bad, papers will use the p-values as a cutoff for this hypothesis testing, but it was really emerging with these ideas about roulette and other games of chance for Pearson. And gamblers got hold of them as well. In the early 20th century, and actually even into the 40s, people would use these methods to record results from roulette tables, identify biased ones, and bet on them. In the 1940s, a mathematics student and a medical student watched the tables of Reno for a few weeks, spotted the biased tables, and made enough money to buy a yacht and sail it around the Caribbean for a year. So really, these biases were there and sufficient to make money. Casinos, of course, started working out what people were doing and made their tables as pristine and unbiased as possible. But this actually had the effect of taking us out of this third level of ignorance and back into the second one, because as some physics students started to notice that the better maintained tables would have, in theory, something that would adhere much more closely to the expected physical laws of a roulette ball moving around the point if you didn't have this real-world noise interfering with your data. In the 60s and 70s, a number of different groups of students got hold of some tables and started to examine what they thought might be predictable. And they observed, if you've ever been to a casino, the croupier will start a ball spinning around the rim, and it'll often spin a few times before they call no more bets. So you've got this window where you can collect information that you can act on if you're betting on it. Eventually he drops down onto a track and then hits one of these deflectors and bounces into the middle. Now, on a European table with 1-0, the house edge is about 3%. So if you're going to make predictions, you don't have to predict the exact pocket. It's a fairly small edge for the house. So even predicting, say, the correct quarter or correct third could potentially give you enough to act on. And these students examining these tables realized that you could collect enough information in those initial few spins to develop reasonable predictions about which region the ball might land in. And they reckoned that they would have about 20% edge over the casino doing this. Now, it's all well and good doing that in a laboratory with a table that you're monitoring and calibrating your models to. It's very different doing that in a casino. Of course, you need to be able to do those calculations in real time, extremely quickly, which is something you obviously can't do in your head or with pen and paper in this situation because you're taking measurements and running calculations off them. So what these teams did was develop hidden computers. And they would, in many cases, have a clicker, so you can see this is someone's big toe, and use this to track. They pick a reference point on the table, because obviously if you've got a table moving and a ball moving, that gives you two potential things to be keeping track of. But if you pick a reference point and use a change of variables, they had it so if they had a ball going past a fixed point, that was sufficient for them on a calibrated model to develop good predictions. It turns out actually that we've got wearable tech pretty much everywhere and really increasing now, but the first ever on-record example of a wearable computer was designed for this purpose, to beat roulette tables. So really, these guys were pioneers in so many ways. But they had many problems. As the first time this was doing it, in many cases they would give themselves electric shocks because they would have wires running to give them signals. They were also incredibly sensitive. They'd have to calibrate their model to a specific table to make predictions off it. And in some cases, if there's a change in the local environment, that could throw their predictions off. On one case, they started losing money and couldn't work out why until they realized there was an overweight tourist who had been leaning on the table and just screwing up their calibrated model and ruining their predictions. So it was a really nice idea, but ultimately one that didn't bring them a lot of profits, and it was more the intellectual challenge of beating this game that appealed to them. And in many cases, sorry.
I heard of one where the guy got acid burns from having lead-acid batteries struck burns.
I think, yeah, there's I think in another case he nominated his wife, but I think she was not so keen on the idea. But really, these stories of people using intellectual curiosity and not doing it so much for making money, but just for the sheer audacity of beating a system, have been around for quite a while. And this was, again, stories that I've been aware of. But for me, the interest in writing the book came around during my PhD, because a lot of these companies who have appeared over the last decade or so, who are not just groups of students trying their luck in casinos, but people really kind of more systematically, in some cases offering betting markets, in some cases providing consultancy to teams or sports organizations. But it seems that this science of gambling has really become more established, and people are running established long-term businesses and putting kind of long-term profits behind it, rather than these kind of one-off attempts to beat the system. And so really, my motivation for writing the book was to try and understand and get a bit more insight into how this industry had developed, and indeed where these kind of games are going, given that we've got this long history of maths and gambling being related. And a lot of the modern, almost kind of hedge fund-esque approaches to betting originated, again, with a familiar game, with card counting. Blackjack is this famous example of something where if you collect information on a deck, you can act on that, because in theory, the cards that come out should be random, but of course they're not. They depend on what's already been dealt, and if you collect enough information on that, that can give you an edge over a casino. And it was really, in the 60s and 70s, a lot of these ideas came out. But of course, as one card counter said to me, it's pretty easy to learn how to card count. It's extremely difficult to get away with it. And a lot of them would get on these lists and eventually just be barred from all the casinos in the world. There were private detective agencies who would just track them down and make life very difficult for them. One of the guys who did this, this is a guy called Bill Benter, about 1920, when he was 19 or 20 years old, when he was going around these casinos, making about $80,000 a year, so pretty good money for a student in the late 1970s. But eventually he just got banned from anywhere. This is a picture from a private detective file on him. But rather than quit gambling, him and a few fellow card counters decided to turn their attention to another type of betting system. And this was horse racing. And it was actually during a visit to a Nevada University library that Benter came across this paper here. This was published in '86. And he calls it the paper that launched a multi-billion-dollar industry. It was written by Ruth Bolton, who's a PhD student at the time. And essentially what they had done is taken a lot of ideas that were bouncing around about horse racing, and I think there was a lot of interest in using newly available computing power and data sets to try and make some kind of actionable predictions for these races. And they essentially took a logistic type model for converting measures of quality about a particular horse into some probability of victory for that particular horse. It wasn't a perfect work. It took them a long time to put together. They focused on US racetracks. And this all had to be entered manually. She said she spent a good year or two just carrying boxes of data around and manually kind of inputting it all. And even so, their predictions weren't great. They had, so the R squared for their model was about 0.09. So really it didn't explain a huge amount of the variance that was going on. But it provided Benter and colleagues with the motivation that there was a method that could potentially work if they just found the right data set. And so they, rather than the US, where you have loads of racetracks and loads of horses, they went to Hong Kong, because this is Happy Valley Racetrack. If you were going to design a lab to study horse racing, it would basically look like Hong Kong. They've got 2 tracks, a closed pool of about 1,000 horses. They run against each other in the same conditions, the same opposition, twice a week, essentially all year round. What's more, there's a huge amount of money wagered. The average track day in Happy Valley takes more than the Kentucky Derby. So it's really a huge amount of money up for grabs and really good data. It's all publicly available that they can play with. And so this is what they did over the coming years, calibrated these models to take this publicly available data and convert it into predictions about the horses. And one of the things talking to them that I found remarkable compared to how I use statistics in my job and perhaps use regression models is they actually have very little interest in working out what bits of data are predictive of horses' victories. So they have these quite detailed models, often like 100 covariates in it. And in some cases, for example, the number of races run might come out as being incredibly important for explaining a particular horse's performance. But really, those teams have no interest in becoming experts in horse racing. All they want is a model that can give them accurate predictions. So they just want a model that gives them a good out-of-sample testable prediction on that data set. They have very little interest in becoming experts. So for me, it was quite interesting that this kind of almost happiness to embrace their ignorance. They didn't want to be pundits and try and impress people with their knowledge of horse racing. They just wanted a model that would give them loads of money. So it was quite an interesting contrast. And there were other issues that came up which I hadn't been fully aware of. And one is how you treat variance in these kinds of races. So suppose we have 2 horses, which according to some model, here's just a simple Gaussian, have the same mean time expected to run a race. But the second horse has some larger amount of variation around it. Now, if those two horses ran against each other and we just drew from this distribution for their race time, it would be a coin toss. They both have exactly the same probability of winning, given these two distributions. So in models that ignore variance between individual performances, if there's two horses, it's not a massive issue most of the time. But what happens if you put three horses in? So suppose we have a third horse with a much larger variance than the other two. In this situation, just think quickly about what you'd expect the differences between these to be. It turns out, actually, that the third horse has about a 45% chance of winning. Because, if you think about it, when it was the first two horses, all it depends is whether you draw from this side of the distribution or this one, whereas horse 3 has a huge chunk of the distribution which will dominate the other two, and then the result is split between the other two horses. I think it's quite an interesting property of multiplayer games, where actually, if you've got the same mean, the high variance strategy is always optimal in a kind of first past the post system. And now I don't want to labour an analogy, but for instance, in politics, if you've got many competitors, actually playing a kind of Marmite high variance strategy, according to this kind of system, is something that's going to give you a much higher probability of coming out first. So I think there's kind of interesting how you deal with variance in these kind of multiplayer games. And indeed, the theory of games, again, can be traced back to gambling. It was really in the 1920s that a lot of this work originated with mathematician, I'm sure you know, John von Neumann. In the 1920s, he was a professor at the University of Berlin, particularly interested in games like in Baccarat and poker, but by a lot of accounts wasn't very good at them. Now, I guess on the face of it, things like poker seem like a kind of mathematician-friendly game. It's a probability of you getting a certain hand, your opponent getting a better one. But von Neumann pointed out there's more to it, of course. As he said, real life consists of bluffing, of little tactics of deception, of asking myself, what does the other person suppose I mean to do? And to study this push and pull between players, and particularly in somewhere like poker, which is zero-sum, everything you win comes out of your opponent's pocket, he realized that there would be some kind of tug of war between the two players. Each would be trying to simultaneously minimize what they lost while maximize what they took off their opponent. And in these situations, you can find an equilibrium point. And this was von Neumann's minimax theorem that showed that in these games, there's a set of strategies which are essentially the best response to whatever your opponent does. So there's this equilibrium strategy where you wouldn't be expected to gain more by deviating from that against an optimal opponent. And this whole theory was really started around toy versions of poker. And von Neumann started with the following two-player game of poker. You've got two players, each given a card that has a value that's randomly drawn between 0 and 1. Two players, one card each. At the start, they both put $1, say, into a pot. Now, the first player has two choices in his simple version of the game. They can either check, in which case both players turn over the card and the highest card gets the money. So from player 1's point of view, they've got a payoff of plus or minus 1. Or player 1 can bet $1, in which case it goes to player 2. Now, player 2 in this situation, again, has two choices. He can either fold, in which case player 1 just picks up the $1 that was already on the table, or player 2 can bet, and then there's $2 in the pot, and the winning or losing just depends on who has the higher card. Now, looking through these equilibrium strategies for this simple version of the game, von Neumann found that if player 1 has a high card, the optimal thing for them to do is bet. Now, intuitively, that kind of makes sense, because if you've got a high card, you want to put money on it, you want to potentially get more payoff. He found that if the first player has a middling card, the optimal thing was to check. Again, that intuitively makes sense that you probably wouldn't win in a showdown, so maybe you want to limit your losses. But in this optimal system, the best thing to do if player 1 got a low-valued card was actually to bet. This equilibrium strategy for the simple version of poker was essentially to bluff if you had a weak card. Now, of course, poker players have been bluffing for years before this, but this was the first mathematical evidence that in these games it's a necessity. It's not a human feature. It's really just, if you just run through and find the equilibrium strategy, that's what it tells you to do. So the specific values here, bet if you're less than 0.1 or 0.9 if you're player 1, and call if you're greater than 0.4. So it's really kind of this first proof that these kind of behaviors can come naturally out of these kind of games. Now, of course, this is an incredibly simple version of poker, and a few others started to look into this game as well. And one of them, who probably actually, because he overlapped with von Neumann at Princeton, was at the time when he was a graduate student, was a researcher, a guy called Alan Turing, who would, in the 50s, actually write an unfinished paper on poker theory, trying to build on von Neumann's work. Of course, Turing's done huge amounts of other work with computing and artificial intelligence, but he was also interested in this aspect of the game. And he made this point on von Neumann's model that there wasn't a raise in it. If you look back to that simple system, it's you check or you bet, and that's an incredibly simplified version of poker. And it turns out that actually has a big impact on the structure of the strategies you want to play in these games, because for the game I described a slide ago, you end up with a pure strategy. You end up with this simple set of rules that you follow. If you pair one and you get a high or a low card, you bet. If you get a middling card, you check. You can just write that down and follow it every time. But as soon as you start adding complexity into this game, you can't always follow a fixed set of rules. You have to incorporate some other mechanisms into your decision making. And to give you a simple example, consider rock, paper, scissors. Now, it might be admirably consistent if you always pick the same thing, but if your opponent works out what you're doing, they're going to take advantage of that. So in rock, paper, scissors, if you want to play this minimax strategy, where you limit your potential losses and make really your opponent's decision as hard as possible, you want to pick randomly. That's the optimal way of making it impossible for your opponent to exploit you. Now, of course, rock, paper, scissors, there's three options. It doesn't take much to spot that the optimal approach in this situation is just to pick a random combination. But poker is far more complex than this. The full version of poker, there's far more combinations to deal with, which means it's not something we can quickly just write down and work out analytically. Fortunately, there is another approach we can take, though, and that's, again, it traced back to one of von Neumann's colleagues, a mathematician, Stanislav Ulam. And a lot of the stories about him, I don't think matched the familiar image of mathematicians in terms of that he didn't really like working through lots of equations and really kind of didn't enjoy trying to find analytic solutions to things quite often. He was once playing solitaire, recovering from an operation, and wondered the probability, if he lays out the cards, that he would end up with a situation where he could complete the game. And he started working through some of the combinatorics of it and very quickly gave up, just realized this was something that he wasn't going to get a neat answer quickly on. So instead, he decided just to simply lay out the cards a few times. Rather than trying to solve it analytically, just simulate it and see what would happen. At the time, von Neumann and Ulam were working on the hydrogen bomb at Los Alamos, and they were looking at neutron interactions, which again was an example of a random system which was very hard to study analytically, but one that if they could simulate those random processes, they could gain insights into its behavior that way instead. Now, because it was a government project, they needed a code name for their method. Because Ulam had a heavy gambling uncle, they called it the Monte Carlo method. Now, of course, this is fundamental in modern science. Anyone who works in computational techniques will use this. We use it in analysis of epidemics. If you have a lot of interactions, it's often much easier just to simply simulate those interactions rather than trying to actually study their properties analytically. And people have also started to use these approaches to look at poker. A lot of the teams, well, a lot of the early poker bots online, the approach that people used was to essentially teach it a set of fixed rules. So this was about sort of 10, 15 years ago. These bots would appear on websites, and what people were doing is they were just coding in this situation do this, in this situation do that. Now, if you do that, of course, your bot is only going to be as good as you are, because you're constraining it by your ability. And Turing, when he first started really outlining his views on artificial intelligence, made the point of, if you're trying to build an intelligent machine, it doesn't make sense to try and build the adult mind with all of its rules fixed and finished. Instead, you want to build the child's mind and let it work out what to do, let it learn itself. And this is what these teams who built these phenomenally successful poker bots have done. They've essentially constructed these bots that can play against each other billions and billions of times and refine their strategy and converge on an equilibrium over time. And actually, they've got so good, these bots, that a couple of years ago, some researchers at the University of Alberta announced that poker was solved. So to be specific here, if you've got a game like noughts and crosses. Finding a solution, finding a Nash equilibrium is something you can actually define. So you can say it's a solved game because we know, for example, at the start of the game, if two players play optimally, that will always end in a draw. And likewise, other games are subsequently solved as well. So checkers is another example. This was about 15 years ago that a solution was presented that if two players play the Nash equilibrium strategy from the start, they will both draw. And what this team had done was show that their bots had converged to a strategy which was, for any kind of finite, plausible length of game, was it couldn't be discerned from the equilibrium strategy. So in other words, they had a bot which wouldn't be expected to lose money against a perfect opponent over any reasonable length of time. So in other words, they had a bot that was unbeatable even against a perfect player. Now, one of the things that's remarkable about this is a lot of people on that team, by their own admission, aren't very good at poker. You know, really, these aren't people who are very keen poker players and have a lot of ideas about how the game should be played. And it kind of goes back to what I was saying about the horse racing teams, that really they're happy to kind of have that ignorance about the game because really these teams are much better at machine learning. And they can develop these bots because they're not letting their pride get in the way and they're letting the bots learn strategies which ultimately are far better. And talking to them, even in the last couple of years, you might have heard a few weeks ago that a no-limits version. So this solution was to a limit version of poker where your maximum stake is capped. A few weeks ago, a no-limit version of the game, which is the more, if you've ever played with friends, is probably the version you're playing. That was also, they had a bot which was beating the top human pros. So these are becoming incredibly good. And they're challenging, actually, ways that human pros play the game. So the strategies, there's one known as limping, where you'll bet the minimum possible in the opening round. So often there's this idea that you should bet or fold in that situation, because otherwise you're kind of just limping along, you're not being assertive. It's kind of seen as a nuisance strategy. It's something beginners do. They don't want to risk any money, so they put down the minimum amount of bets. But these bots do limp sometimes. This strategy that for years poker pros have said is rubbish and only beginners do it, they're now being beaten by bots that do it. And there's a lot of other examples, and one of the other things that comes up a lot is that bots seem to bet big on hands that humans would often fold, or bet small on hands that humans would go all in. So it seems their version of the game, their abstraction they're using, seems much broader than humans, and that we seem to lump how we play poker into certain situations and kind of go with folk wisdom, whereas the bots are exploring a much wider range of options, ultimately more successfully. Now, this is a fantastic achievement calculating these equilibrium strategies, but there is a flaw with it, and that's that if you're developing an equilibrium strategy, you're assuming that your opponent could be perfect. You're developing an assumption that your opponent is highly rational and flawless, essentially, at the game. And if they're not, and they do have quirks and flaws, then potentially you're not fully taking advantage of that. If they have predictable behaviors, then potentially there's something in there that you might want to exploit. Now, the converse of that is that if you develop a bot that does exploit human behaviors, and you have a very good opponent, they could in turn take advantage of you. So imagine you're playing a game with somebody and that person pretends to be a beginner and a novice and is very passive, doesn't know what they're doing. You might adapt your style thinking that they're very easy to take advantage of. And once they've sort of become comfortable with you learning that image of them, they could then adapt and become far more aggressive and far more competent, knowing that you've learnt the incorrect image of what their version of play is. It's not just poker that happens. Last year, Microsoft introduced an AI bot to learn and interact with Twitter users and learn how to speak and how to interact and improve its language skills. Twitter users had a different idea, though. Basically, within 24 hours, Microsoft had to take their bot down because the users had taught it so many horrendous views and such an incorrect version of the image of what they should be presenting. So even these quite advanced bots can be led astray by these. Yeah. But really, they can be led astray by these kind of ideas. And it's not just in these situations with very advanced bots that have spent huge amounts of time learning. Frequently, for example, in finance, the bots that are used are far more simple. And there's a story a few years ago in 2007 in Norway where two Norwegian traders had noticed that a US stockbroker used an algorithm that would always react to trades in the same way. So even if the trade was massive or tiny, the algorithm would change the price the same amount. So you can imagine that what they did is they put lots of small trades in to drive the price up, put a big trade in, and then made a huge amount off the broker. Now, they were taken to court for that and charged with market manipulation. But really, it kind of built up a lot of support in Norway, and they're kind of seen as Robin Hood figures stealing off these kind of rich American banks. And on appeal, their lawyer made the point of, had they been dealing with a stupid broker who was doing that, there would be nothing illegal about that, no market manipulation. The fact they were dealing with a stupid algorithm who was created by a broker who probably hadn't been thinking through what they were doing wasn't necessarily a reason to penalise them for manipulating anything. And actually the court found that as sufficient evidence that you can't, in that situation, penalise humans for exploiting a stupid robot that's created by a stupid human, maybe, when you wouldn't be penalised for just directly exploiting the human. And it's not just this situation where these kind of simple algorithms can run into trouble. A great story from a few years ago was the early poker bots, the early poker websites. And what one of them did is in the late 90s, to show how rigorous and transparent their online card room was, they published the shuffling algorithm for their online poker games. And they thought, great, transparent, everyone's going to know our game is completely fair. Now, if you shuffle a card deck completely properly, you're going to have, obviously, 50 factorial combinations, just something that you could never tackle by brute force. Perfect shuffle is something that you're never going to be able to exploit. But some people went through this and spotted that there was a bit of a flaw in it, and it's around this thing, that they generate a new seed based on the system clock, which at the time was in milliseconds, which could only generate one of 86 million possible numbers. And it got worse than that, because these coders realized that they could actually synchronize their clock to the system clock on this server, which then brought them down to about 200,000 combinations. And now suddenly we're in territory where brute force could come into action. Now in a game like Texas Hold'em, you get dealt 2 cards at the start. So you already know 2 cards in the possible deals that have come up. What these guys actually found is that as soon as you saw 5 cards in total, you could identify which of these 200,000 shuffles it was. And obviously if you're playing no limit poker, as soon as you've got the first 2 and seen the next 3 appear, you now know the order of everything else in the deck around the table. So of course, these guys did quite well. But I think it just shows that we can have these things that we think are seemingly random, but actually there's these inherent flaws, and if you're not careful, there's really kind of things that can be exploited by smart people. And I think that's a theme that comes up really often in these kinds of games. I think there's a tendency, particularly in the media, and I think just in common perception of these things, to put things in neat boxes. That we had a box where this is random, this is all luck, this is all skill on this side. I think there's also a tendency that if something goes well for us, it probably goes in this box. If something goes badly, we probably stick it in that one. But these games, and I think it's probably familiar to most of us, but I think it's something that doesn't get enough discussion, is that we're really dealing with much more of a spectrum, and that as we've seen, these games like lotteries and roulette, that things that are really kind of renowned for being the height of luck can be beaten with sufficient effort and sufficient skill. But even games that we have the reputation for being purely skill can also be a bit more complicated than that. There was, of course, the famous example in '97 of IBM's Deep Blue chess computer playing Garry Kasparov, this landmark of man versus machine. And early on in the game, Deep Blue made a move which, by all accounts, threw Kasparov. It took a rook, which at the time didn't seem to make sense. It was a move that Kasparov said that he couldn't see why Deep Blue would be doing that. There was no obvious route for it to make that decision. And it kind of persuaded Kasparov that he was just dealing with something that was completely beyond his perception of the game, that it was just making decisions that he couldn't even comprehend how it could be doing that. It turned out that Deep Blue didn't pick that move because it identified it as being extremely clever or nuanced. It actually run into a situation where it couldn't, of the set of possible moves, clearly identify what the best one was. And in that situation, to avoid hitting a dead end, it had been programmed to simply choose randomly. So that move, which shaped this game and this really kind of landmark event in skill of humans versus machines, was influenced by this chance outcome. I think this really kind of illustrates the value of looking at these games and throughout history, and even now, as we're seeing with AlphaGo and a lot of the new poker software, why it's so interesting and why it can be mathematically so useful to study these games. But I think we also need to be aware of another reason for doing it. I think Alan Turing summed it up nicely when he was looking at games to understand intelligence, and he said, it would be disingenuous of us to disguise the fact that the true motivation for the work was the sheer fun of it. So, thank you.